So robotics is really a long history that we say industrial robotics started in 1961 with the Unimate. But imagine how many robots we have today. We have millions and millions of robots running all around the factory floor, and we are seeing a lot of new robotics coming in different fields. In the medical field, we are seeing robots coming closer to the human in social robotic interaction that is bringing VR and touch and different modalities. We are seeing robotics bringing support, human augmentation. We are seeing a lot of development in service robotics. And this is not the whole story. We are just about to start in moving robots to the challenges of environment that are not reachable by human. So I'm going to tell you a story about La Lune and our expedition on the Lune, and this would illustrate a little bit that part of the development taking place in robotics. So La Lune is this vessel of King Louis XIV that sunk off the coast of France, Toulon, in 1664. It was only discovered in 1993, so very recently, centuries after. Now, this vessel is sitting at 91 meters, and at 91 meters, you cannot send divers. You can send diver to 30 meters, 40 meters, maybe a little bit more, but it is really, really hard to send divers to do any work in archaeology around this. So what we use is a suit in which we place a human. That suit is very rigid and very difficult to maneuver. And the operation that we are talking about is going to involve contact and touch and physical motion. In fact, if we go to offshore platforms, and if we think about what is happening in many of those applications, we can see how much difficulty we have to reach, even to maintain the structures that we have in the water. So these are the offshore platforms, the oil platform on the North Sea. And in order to maintain those platforms, we have to train divers to go to 130 meters. 130 meters inside this capsule. But to get there, they need to be conditioned for a whole week with a mixture of oxygen and helium, and then they will be able to reach that area. So this is the vessel where they are going to sit, and then from there they will go and do the work, and then they need another week for decompression. So this is for 130 meters. Well, 130 meters is a little shallow for what exploration in the deep sea and oceans are. And one of the most wonderful things that we have done was really to build a lot of robotic systems that would allow us to explore the oceans and see and discover. But the problem is we didn't really manage to build the capabilities to do. So we can see, but we cannot do. And in order to manipulate and in order to repair underwater, we need bimanual capabilities, and that's what brought the idea of building a robot as Ocean One. So Ocean One is this platform that we developed with a concept that keep a connection with the human, because this is almost like surgery, going underwater in an unstructured environment. It's very, very challenging task that the autonomy of the robot, how high it is, it's not going to allow the robot to perform all those different things. So we need the human. And the concept brings a connection between haptic devices, you see two of them here, with the robot. So a haptic device can allow us to interact with the robot and let the human feel what the robot is touching. And in that way, we are going to have the diver sitting on the boat or wherever, connected to those haptic devices, and then allowing the human to interact with the robot deep in the water. So Gerald actually is over there. He's going. Could we show just a small piece of that interaction that we could have? Gerald is going to run this in a virtual environment, so we are going to simulate the robot, and we are going to be able to see how that interaction is taking place. So if we can switch to the other screen, please. All right, so here is Ocean 1 in simulation. In fact, that simulation environment allows us to simulate any robot and develop the controllers and interaction. Would you like to go for a treasure hunt? Anyone? All right, let's go for a treasure hunt. And now the robot is, oh wow, look what we have there. Since we don't have time, why don't you go up and get, so we can change the view. Now we can go to the view from the eyes of the robot, and now what we are going to see is how the robot is going to, the human is able to interact with the robot and feel, can you grasp this? And drop it. And when you are dropping objects, you need to solve and resolve contact and all of those things. Could you push it around so we can see the contact? Simulation. So this is simulations underwater of the robot with interaction with the human, allowing the human to assist the robot, in fact, to help the robot, to guide the robot with the human experience, knowledge, and intuition, while the robot has all the abilities to do the coordination and all these different things. Thank you very much, Gerald. Bravo. That was... especially Gerald is doing this in 2D, and usually we have a 3D display, so you can really manipulate things in a very effective way. So just I wanted also to mention, how amazing the students are in assembling a robot like this for underwater. Here is the students in the lab working and building the robot. That took us, a little while, about 3 years. And here is the simulation with the full haptic devices, the 6-degree of freedom haptic devices that we use. And then you have to remember, this is a 200-kilogram machine that we need to take to the pool to test it. It cannot test it in the air, so we have to push it all the way, and then we discover problems we have to solve. We'll bring the robot back and forth until finally the robot was ready for that mission. So the mission was about extracting artifact from La Lune, but this project started actually for many other applications, including the environment, coral reefs, including operations, maintenance underwater for structures there. And also, this whole project is an example of what can we do if we connect human with the machine in a meaningful way. So think about high-altitude stations, where we need to service the stations. Think about mining and how we maybe are able to now remove the person who is doing there, sitting there to a safer place and interact with a machine that is in that area. Mining is very costly because we have to create living environment, oxygen, cooling, and this is also true for many of the disastrous area where we really need to intervene and operate and replace human. Now, robotics has been bringing a lot of development in mobility. Mobility has been progressing in an amazing way, and the question is, how can we go beyond that so that we are able to do things? So I always like this example of Ashimo, the amazing machine in terms of mobility, but when it comes to manipulation, it is not an easy problem. The reason is we continue to program robots the way we programmed industrial robots. That is, we spend a lot of effort programming all the details. We program this robot at the lowest level. And the question is, how come a little child is able to do it? What are those skills that the child has, and what can we do in order to understand those skills and map them to a robot? So programming was fine when we're doing over and over the same thing. However, in those environments, we are going to need skills, and skills that would allow us to program the robot at much higher level. So manipulation skills are things that we can, first of all, we can understand by looking at human. But what we discover is that actually we need to change completely the modality of the control, which is typically a position control modality, into a compliant motion control modality. And that compliant motion modality doesn't rely on precision and accuracy and allow us to perform tasks in very efficient way, dealing with uncertainties, learning complex tasks, and performing them by the robot very quickly in very different environment. Learning about the human is very important, as well as we need to communicate and understand and cooperate with the human. Learning about multi-contact, learning about the posture of the human or the humanoid robot, learning about all the constraints that we need to put. All of these are very challenging. And finally, once we address this and see the needs to do that in real time, we realize the complexity and the challenges. And again, the human model brought a lot of interesting concepts that led to a constraints-consistent whole-body control framework. Those algorithms allow us now to take a humanoid robot, interact over multiple surfaces, slippery surfaces, maintaining the reaction forces, balancing the dynamics. So instead of building a system where we are planning all the details and executing at the lowest level, where this is actually not going to work because the planning is so expensive that we are separating the two systems, that is, we plan offline and execute online. We are building a system with capabilities of whole body control that are connected to the human in a way that is understandable by the human, and the commands of the human are sent back to the robot in a way that are understandable by the robot. This loop of interaction between the human and the robot allow us to bring that powerful capabilities on the robot to perform very challenging tasks, at the same time interact easily with the human that is guiding those motions. So here is an example of how far we can go walking up as we are rock climbing, adding tools to the robot so that the robot can walk in those environments and stably, instead of walking just with biped. So back to Ocean One, and beside all the development in its dynamic control, underwater hydrodynamics, and all the different characteristics, now we have the robot ready to go to its mission. And we took the robot, we put it in a box, we send it to the Mediterranean, we lower it in the sea, and there the robot is really happy. It turned out the robot is much happier in the sea water than the pool for some reason. And first we didn't want to lose the robot, so we put it in 15 meters so it can interact with the divers, and the robot was demonstrating really amazing characteristics at 15 meters that we felt, well, it's ready to go. So we send it to 100 meters, and there the robot starts navigating. These are two cannons where the robot is approaching, and you can see this vase that the robot was aiming to take. And as the robot was maneuvering, the robot got caught under the left arm, get caught under the cannon. And it was midnight, and the captain said, we have to leave. It is very dangerous now, the water. And I looked at this situation and said, no way, I'm not leaving the robot there. And no one can come and rescue the robot. And I'm mentioning this because it's really important to realize the importance of the a human form, projecting the diver form into the water. This embodiment that came through the body of the robot. So basically, I realized if we just push with the haptic device down, then we will be able to kill the, I killed my phone. We were able to release the robot from that configuration, and the robot, in fact, jumped. So you can see how happy I was there. Now, I'm going to just show you the treasure that we brought. It is a treasure from a Catalan vase from 1664. And here is the movie showing the story of, and it's a very short movie. Can we have the sound? Yeah. So one thing about the seawater, different from the water in the pool, is the fact that you are going to have more buoyancy. And that really was suitable for the robot. Once the robot was in the water, immediately the robot actually was swimming much better than the pool. And the robot here is supposed to be not connected to tetherless, but we used a tether because the mission lasted for 7 hours and the power was only 1 hour. So the robot is now interacting with divers. At the same time, it is controlled haptically from the boat, from the surface. And collecting different objects and moving them. So once the robot was ready, the diver, Olivia, was telling the robot, now we are ready, you can go, and I'm going to... So now we are going to move the robot all the way to the 100 meter. So it's quite dark as you move. The sea is very dark, and that's why we placed already a light down there. Here is the robot arriving to the site of the two cannon. You can see as you come very close to the seabed, you raise all the sand, and now the robot is completely lost inside the sand. And that's when the robot gets caught between the two cannon. The fish is scared by the robot. You can see Hannah, how she's like just, oh my God, what's going to happen? And now we're going to push the arms against the surface so the robot will free itself. And now the robot is coming out of this magically. So the next day we had the robot going to the site again, and the robot located another vase and brought the vase to the container. So the idea is with the container will go to the surface autonomously with the floats. And here is the two hands of the robot holding the vase. And now we have to just close the container, place the vase in the container and close it, and the mission is done because the rest is autonomously done. So here we are placing the vase.
Oussama, tu peux fermer le couvercle avec le bras?
So just we need to close the container. 1, 2, 3. Yeah! Amazing. So I'm going to ask you a quiz. You have to tell me who touched this vase after 4th century first. Yeah. So this is really an example of an amazing performance for a machine that was built in a laboratory and deployed in the real field. Champagne for everyone, including the robot. Thank you very much for your attention.